Hello everyone. It's our pleasure to have Dr. Hatice Güneş from University of Cambridge as our speaker this week. I'm very happy to introduce Dr. Güneş because we recently started collaborating with her, and this collaboration has been very fruitful. Our collaboration started actually last year with my sabbatical in Cambridge. However, because of the pandemic, it was cut short and I had to return early. However, we had started working together on several projects and we were able to continue our collaborations remotely, and we are still continuing our collaborations on lifelong learning and effective computing problems. Let me go over Hatice's biography. Dr. Hatice Güneş is a reader in Effective Intelligence and Robotics, in short, AFFECTIVE, and the director of the AFFECTIVE lab at the University of Cambridge. Department of Computer Science and Technology in the University of Cambridge. Her expertise is in the areas of effective computing and social signal processing, cross-fertilizing research in multimodal interaction, computer vision, signal processing, machine learning, and social robotics. She has published over 100 papers in these areas. And Dr. Hatice Güneş is the former president of the Association of the Advancement for Effective Computing, the general co-chair of ACII conference, which is one of the important conferences in effective computing, the program co-chair of HRI 2020, which is also an important conference in effective computing, and the IEEE FG conference. She was the chair of the steering board of the IEEE transactions on effective computing in the period of 2017 to 2019. She has also served as the associate editor for several journals related to effective computing. Her current research commitment is to embrace the challenges present in the areas of health and well-being and empower the lives of people through technology. In 2019, she has been awarded the prestigious EPSRC Fellowship to investigate adaptive robotic emotional intelligence for well-being, and has been named a faculty fellow of the Alan Turing Institute, which is the UK's National Centre for Data Science and Artificial Intelligence. As I said before, Dr. Güneş's presentation will be by streaming the recording that she provided to us in order to not face any technical problems. At the end of the video, at the end of the streaming, Dr. Güneş will be here with us for your questions. So let me start.
Hatice Güneş. I'm a reader in Effective Intelligence and Robotics at University of Cambridge, Department of Computer Science and Technology. And today I will be talking about artificial emotion.
How is the sound? Is it okay?
Not bad.
Sorry?
Not bad.
Okay.
Could be a bit louder, but...
It is the maximum
okay.
On my side.
Okay.
Intelligence for well-being. This very much relates to nonverbal social signals and how we communicate using these signals with one another. So the nonverbal communication has two aspects. So we have the sender end and the receiver end. The sender constantly generates certain signals, such as the way they position themselves with respect to others, the way they use the space, the orientation of their body, the way they dress, the way they gesture, the way they speak. And these are interpreted on the receiver end, either consciously or unconsciously, for various things like forming first impressions or deciding the social role of the person and interpreting their expression of emotions and so on. Artificial emotional intelligence constitutes of three parts, and I will explain this later on. So here I'll just cover those three. So eliciting expressions or regulating attention or drawing out a reaction in the user, so making the user feel something. The second is expressing emotions and social signals that can be identified by humans. And the third one is automatically detecting emotions and social signals of humans. Let's look at the example. The example comes from the Semaine project. This was an EU project I was involved in as a postdoc. And this comes from our latest paper in 2012 that combined all the aspects of the system. So the idea is this is a fully automatic or fully autonomous system with sensitive artificial listeners, where the goal is the agents have different personalities and different emotional moods, and they will try to create and sustain an interaction with the user based on analyzing only their nonverbal behavior. And the agents are four. They each have their own distinct personality and emotions. So Poppy is extrovert and happy. Spike is slightly neurotic and sad, and Obadiah is gloomy, and Prudence is, as a matter of fact. So this was the first fully automatic framework to have this closed loop interaction, so to automatically interpret, analyze the user's affective state, and create corresponding responses. Here, let's look at it a bit more in detail. So we have the camera and the microphone to sense the user multimodally. From this sensing, features are extracted at different levels, and individual analysis results are fused, and then this interpretation is sent to the dialogue manager. The dialogue manager keeps a history of the state of the user, the state of the agent, and the state of the dialogue, and based on this proposes appropriate action and behavior to be played by the agent, considering the current agent identity and their personality and mood. And once this is played, again, the sensing of the user is continued. So this is a closed loop interaction that keeps going. I will now play an example so you can see how this is done in real time. So here, the system constantly evaluates and assesses the communicative signals of the user, like head nod and smile. And then we have the personality of the agent, that is Spike, that's neurotic and extrovert. And the emotional mood of Spike is angry. And what happens is, because Spike wants to make the user angry and draw the user into their own emotional state, when the system assesses and understands the user is nodding, Spike would shake his head as back channels or bend his head. So let's take a look at the video. Here, just to let you know, it's put side by side, but in the original framework, of course, the user wears the microphone, as you see, around their ear, and they're looking at the screen where the agent is interacting, and there is a camera to sense them attached to the screen as well.
Well, I'm Spike. What's your problem?
I don't have a problem.
Is that so? Tell me about it.
Well, you know, nothing's going
I
terribly
suppose you
wrong.
really think you're something.
No, not really.
How can you believe that?
Quite easily. I'm not up myself, I'm not spoilt.
Well, I think you're wrong to be so pragmatic about it all.
Really? Well, you're not always right. I'm not always right. So. Yeah.
I think this gives you the impression of how this communication takes place. Example application of such sensitive artificial listener or virtual agents is the SimSensei that was created by the University of Southern California much later after the main project. Here, the purpose is automatic behavior analysis in clinical settings and used for healthcare support. So it's a good example for how these agents can be used for well-being. So you can check out the link and also the relevant paper as provided on the slide. So we already have an understanding of how these three different aspects of artificial emotional intelligence were taken into account in the creation of the agents. But we will focus a bit more on these two aspects. So the expressing of emotions and social signals that can be identified by humans. This relates to emotion theories. So there are many emotion theories, and here I will just cover the ones that are used by computer scientists and affective computing researchers. So one of the first and most influential ones has been the evolutionary theory by Darwin. So Darwin traveled around the world and analyzed and observed how animals and humans express emotions through their body, their face, and he stated that emotions were really useful for solving evolutionary problems. But since then, of course, particularly in the last 25 years, researchers have really understood beyond this that emotions are actually very important for almost everything we're involved in, because we always feel something, so they affect the way our motivations work, how we make decisions, how we actually learn, all of these aspects are impacted by emotions. And the expression of emotions can be done in different ways. So we can have physiological aspects like the breathing, the heart rate, even the brain signals, and the audio aspects, the way we talk and the way we pose, how we use intonation. But the visual channel is the most important one in our social communications. And in the visual channel, we have the body, so we can express by a posture, gait, and gestures. And then we also have the face. Face is the most influential channel for expressing the emotions. Here you see the 6 basic emotions that were popularized by Ekman as the universal categories of facial expressions. So these are fear, anger, sadness, disgust, joy, and surprise. And here you see a really exaggerated, fully blown up representation of those that have been recorded in laboratory settings. But this has limitations because in daily life we don't express only these 6 basic categories, and not every emotion has a distinct facial expression, such as awe, guilt, and shame. And due to these limitations, other researchers came up with the idea of representing emotions as dimensions. So here we see Russell's circumflex, and there are 2 dimensions, arousal and valence. Arousal relates to how active or inactive the emotion is, and valence relates to how positive or negative the emotion is. And we can of course map different categories along these dimensions as needed. Now let's look at how from this background knowledge we move towards robots expressing emotions. I'll show some early examples. Here you see Kısmet expressing some of the 6 basic emotion categories. This is one of the earliest robots. Then you see Philips iCat exactly showing the 6 basic emotions that we already have seen in the previous slide. And then moving from those more recently, the full body aspect has been incorporated into robots. So using posture and gesture and even gait, we see now robot and later on Pepper. But there has also been work investigating how expressions can be synthesized on the robot side via lights and sound. So now let's open up this creating artificial emotional intelligence aspect a bit more. So as we already have seen in the previous examples, we have the user and we have different sensors to sense the user. So visual, audio, even biosignal processing. And from this, now we need to use all these background research theories that I covered to be able to then acquire data. So we need data to be able to train models, and this data needs to be annotated, and then from the data we extract features and then train machine learning models for prediction and recognition, and these are then evaluated. The feature extraction and recognition part with deep learning of course has been integrated in end-to-end models, but more or less the architecture is similar. But we don't stop there. This is not enough. So once we interpreted, for instance, that the user is smiling, we need to be able to understand the context. So is this a smile of embarrassment or is this a smile of enjoyment? The only way to know this is to be able to have an understanding of the user context. And context relates to W5 plus questions. So who the user is, what they're doing, where they are in terms of environment, why they're doing certain things, how they feel, what are the social signals they're displaying, and so on. So once we have this interpretation, then on the agent or interface side, we can create context sensitive and responding and adapt the environment and the behavior of the interface based on this. Here the example is a virtual reality gaming. So this is one of the research areas that we have been working on, affective virtual reality gaming. And the motivation for this comes from neuroscience. So we did some collaboration with the neuroscience department in Cambridge, particularly people working on dementia and working with target user group of people prone to dementia. So it's one of the highest priorities for healthcare systems worldwide. And cognitive training is considered as one of the preventive interventions. But of course, there are issues with this. So both with computerized or non-computerized method. So with computerized methods, it is quite good and people do it, but adherence after a while is low. And therefore, virtual reality is seen as a potential solution to keep the people or the users immersed and more engaged. So the first study I'll be talking about is effects of valence and arousal on working memory performance in virtual reality gaming. So this study employed 30 participants and a custom-made video game was created called Memory Break. And this had two versions, desktop and virtual reality version, because we wanted to evaluate how these two engaged the users similarly or differently. And when the users came for the study, their working memory capacity baseline was measured with certain tasks that is well known in the literature. And then when the participants started playing the game had different difficulty levels. They would report after playing each difficulty level in terms of how they found the game. So they did the in-game experience questionnaire, but they would also self-report about their affective state. And the participants played both the desktop and the virtual reality versions with 1 week in between. So they would be randomly assigned to each condition, and then they would leave 1 week before coming and doing the other condition, again with 3 difficulty levels. The game Memory Break has 3 difficulty levels, aimed to evoke 3 different levels of arousal. Each difficulty level has the same memory load. So every 30 seconds of gameplay, the game stops at a door, and then a random sequence of letters appears that has to be remembered. And the user keeps playing, so they throw the ball, trying to avoid certain obstacles, but they also get points with diamonds and so on. After 7 seconds of gameplay, the player has to recall and input the letter sequence shown. And the ultimate goal is to obtain the highest score possible. Now let's take a look at the video prepared by Daniel. So we'll take a look at the virtual reality version. So this is level 1. They start playing, and you see how they use their hands as input while they're interacting in the environment. We have some sensors, and there are some underneath the t-shirt as well for the heart rate physiological signals. Lip motion is being used to get the input. So the first level is quite easy. Now with the second level, you see that things start getting faster and more challenging. So they have to do more actions. And now with level 3, this is the most difficult level. And while you observe, also pay attention to the other hand of the person. So their left hand, you see, it starts to get quite tense. The thumb is being raised. This is something we did not expect when we were doing the design of this study. So the person is challenged, and you observe the tension through the other hand, which they were just holding. I'll skip the desktop version, but things are quite similar. Now we will look at some of the analysis of the results. So in terms of working memory, first of all, the people were divided into 2 groups based on their working memory capacity baseline: high working memory and low working memory. What we see in terms of results is participants with low working memory had a significantly better working memory performance playing in VR setting, so the main finding. But this was particularly pronounced for levels 1 and 2 that you see here, highlighted with the orange rectangle. These are in red and green, and you can see how the performance is quite high and increasing. Now, looking at working memory and valence and arousal, the results indicated that valence level is significantly correlated with working memory performance. And then highest arousal was observed in the 3rd level. And participants achieve their best working memory performance when both valence and arousal are high. So we see this particularly strongly highlighted here for the low working memory capacity group. But we also need to pay attention that for level 3, arousal is keeping on increasing, of course, because it's challenging, but the valence is actually decreasing. And this relates to the theory of flow. Here, the idea is when we create games, the idea is to engage the user and keep them in a state of flow. So this is a region where the player ability should be used to the fullest, so they feel that their potential is being used, so they're engaged, without falling into the boredom area, but without forcing them to fall into the anxiety area where they feel they're being challenged, but they can't handle it anymore. And this is indeed what we saw in level 3, when the person was moving their other hand and the tension was quite obvious in there. So the ultimate goal is really to keep the players in the state of flow. And working memory performance can improve when the player is in a state of enjoyment, and this relates to having both valence and arousal high. There are some limitations of this study. So first of all, abstract cognitive interventions improve performance on training tasks and closely related tasks, but it's difficult to really have them generalized to real-world performance when things are, and the tasks, the environment is different. And also, instead of a fixed difficulty framework, dynamic adaptation is much better and is preferred. So the second study is a gamified approach to cognitive training using VR and affective adaptation. So here, the main idea is that we do sense the player using physiological sensing, and then this data is being interpreted after feature extraction, is being sent to the machine learning model for affect classification, and based on the classification of the player's affective state, the game needs to adapt accordingly. So this is the affective feedback loop employed in affective games. So for this study, there are 2 tasks, and this here the idea is to try to make it as realistic as possible. So for the working memory task, it's a virtual supermarket, and for the episodic memory task, it's a virtual multi-room museum. So for the working memory, here you see the details. The goal is to find a randomly generated array of products in a shopping basket inside a virtual supermarket. The products are specified to the player at the start of each round, and each product on the shopping list is displayed to the person as an image and test description. Players are challenged to remember the remaining items on the shopping list while they actively search for each product, and the number of products to be collected is determined by the difficulty level. So the medium difficulty task would ask the user to find 7 products, and this is intended to be the most engaging and balanced difficulty for most users, also based on Miller's magic number 7 plus or minus 2. And then the easy and hard difficulties task the users with finding 2 or 12 products respectively. And these difficulties were really designed to increase the likelihood of inducing negative effect in the users, so trying to really map them into these different regions or the circumflex. When we move towards the episodic memory task, this takes place in a multi-room virtual museum environment, and the task is divided into 2 phases. These are consecutive. So the first one is the encoding phase, which is about storing information. And then the second part is retrieval phase, and this is about recognition of previously stored information. In the encoding phase, the players are asked to search for 1 or more displays at the randomly generated locations in the museum. So players interact with the marked displays in this phase. They use a laser pointer, and then the age of the display would be shown to them. And that creates a greater degree of spatial context to be encoded. And after all the marked displays have been interacted with, the game transitions to the retrieval phase, removing the marked displays from the museum and also teleporting the player back to the entrance. Now, in the retrieval phase, players need to place a subset of the displays they interacted with back in their original positions, and they can use the laser pointer to indicate where in the environment they think it was located. So the data acquisition was done from 18 participants, and in the virtual reality environments, we need to bear in mind that the face is occluded, particularly the upper face. So if we want to measure what's going on with the facial expressions, this is a bit challenging due to the obstruction. So we work with MTech, and we used basically facial EMG for facial expression analysis by placing sensors inside the headset. So these are being used to record the muscle movements of upper facial features. Then, as people play the game, again they self-report similar to the first study in terms of arousal and valence. And time and time frequency domain features were extracted. The full set is provided on the right-hand side. And in terms of classification, different experiments were conducted. So either approaching it as a 4-class problem, so having these quadrants of valence and arousal. So excited, happy, angry, frustrated, boredom, depressed, relaxed, calm. Or as 2-class problem in terms of valence, high-low, and arousal, high-low as well. Best results were found with KNN. Here, the 4-class results are not presented, but KNN provided best results in terms of arousal around 76% and valence around 64%. So some of the findings, talking to the people qualitatively but also quantitatively, so there's a need for a trade-off between ecological validity and engagement, because majority of the participants expressed a preference for the museum environment. But in terms of preference for the tasks, these responses were evenly split. So many preferred the episodic memory task because the gameplay had more variety, but others appreciated also the fact that the working memory task in the supermarket was quite naturalistic because they could physically touch items to pick them up or lean across shelves and so on. Then the next step was adaptation. As we already mentioned, the adaptation really intends to lead the players to a flow state. This particular study created the adaptation based on a rule set, and this was tested with pilot participants. And the rule set goes as follows. So if the sensed state of the participant is calm negative and the score is perfect, then the idea would be to challenge them a bit more because they're doing very well. So the difficulty level is incremented by 2. If the person is in calm negative and the score is imperfect, or it's positive valence and they have a perfect score, here the difficulty will be incremented by 1 because they're either in a positive valence or they're not performing that great, so they have imperfect score. The third rule is if there's positive valence and then the score is imperfect, no change in difficulty because they're still enjoying it even if they're not really getting the full score possible. Then if the user has negative score or they have an imperfect score but they're in energetic negative state, then here we are seeing that they're not doing that great, but also they're not enjoying anymore. Therefore, we need to decrement the difficulty. And the final rule is about realizing that the user is in an energetic negative level, and then the score is also negative, so they're really not enjoying it, and the score is also not great, so they're not doing well. Then the difficulty is decremented by 2. Then after this adaptation was implemented, an intervention case study took place. This was with the help of the neuroscience department, and the idea was to have older adults take part. They played both the adaptive and the non-adaptive version of the game, and this was in 2 15-minute gameplay sessions, so 7.5 minutes for both working memory and episodic memory tasks. And to mitigate any order effects, basically randomizing the order. And their subjective experience was also evaluated by asking them to fill in-game and post-game components of the game experience questionnaire. And each session was concluded with an informal interview. And here we see the results. So here what we see is in the adaptive version, there is an increased feeling of competence as reported by the people, but also some decreased feeling of challenge, but with some increase in the feeling of flow. So what we can say is that the adaptive version worked as desired because it did provide this sense of flow to the people, and they really felt competent as well. And although the challenge seemed to be decreased, it actually is balanced with the fact that they're still feeling competent and in the state of flow. Of course, these findings need to be taken with caution because it was only 6 participants. The next thing I will be talking about is human-robot interaction and some of the studies we have conducted as part of this, and in particular telepresence robotics. Telepresence robotics relates to humanoid robot avatars. So the idea here is that the robot is not autonomous. Instead, it's operated by a human. In this case, human is wearing a virtual headset, so they see through the robot's eyes, and then they move their hands and head, and they even talk, and this is replicated or projected onto the robot. Usually, they're not collocated. In this example, just for simplicity reasons, it's captured together. But in actual applications, the locations are separate, and that's the whole idea actually, to have a robot to represent what the human operator would do. And telepresence robotics is an alternative means of communication and has been used during the pandemic as well. You might have seen how robots represented students in Zoom graduation ceremonies for different universities. And also in the UK, in the Hastings Museum, a teleoperated robot was used by people to go around the gallery and see different paintings. So you could actually sign up and you would be on a list, and then you could be assigned to a robot to go around and give you the experience of the gallery. But also in elderly care homes, they have been used to help residents stay in touch with their loved ones and their family. This is another example. This is from before COVID times, about an alternative cafe that opened in Tokyo and was staffed by paralyzed people that controlled the robots by the interface that was created for them. So in summary, telepresence robotics has a lot of potential for different applications. Here I will briefly describe a recent study we have conducted about creating a robotic coach for mindfulness and well-being. So this study is a longitudinal study, and in human-robot interaction, most of the studies are conducted as a one-off or very short-term studies. And here the longitudinal aspect is already a challenge because we need to ensure that people attend without dropping, but also we need to ensure that we are able to engage the people throughout these longer time intervals and periods. So it was a study for 5 weeks and consisted of 5 sessions with 1 session administered each week for about 30 minutes. And each session focused on a specific topic, and the 5 sessions together are designed to provide an introduction to mindfulness techniques and also suggest how to integrate this into the daily life. So we worked with a very experienced human coach who structured the sessions. There were 2 conditions, so where 4 to 5 people interacted face-to-face with the human coach, so that would be one condition. And the second condition, again, 4 to 5 people interacted this time with the teleoperated robot coach. In total, we had 19 participants, around 9 to 10 participants per condition, and 4 to 5 participants per group. Here is an example image of how this took place in terms of teleoperation. So the human coach and the robot that is being teleoperated are in separate rooms, and we see at the head of the people, so they're already doing the session with the teleoperated robot. And then through various algorithms, the coach is able to see through the robot's eyes because they're wearing the virtual headset, and the images gathered through robot's cameras are projected onto this headset. And when the person moves their head or they gesture, these are projected in real time onto the robot. And also there is the talking aspect and listening aspect again through the robot. And then we tested 3 hypotheses. Perception scores of human coach do not vary significantly with time. The second one is perception scores of robot coach change significantly with time. And the third one is mindfulness sessions promote relaxation and calm in both human and robot coach sessions. To investigate hypotheses 1 and 2, we used random coefficient modeling, which was found to be very useful when we analyzed longitudinal data with both inter and intra-individual variability, and at times even missing data points. So let's take a look at first the hypothesis 1. So what we see here is that how the impression ratings and interaction conversation, interaction sensation ratings based on the questionnaires that people filled vary over time. In summary, there is not a lot of variation. So from early on, people rated the human coach high in terms of all these different aspects. And this stayed quite consistently high over time. And this is not surprising in a way, because the human coach is experienced and has been doing the mindfulness for quite a few years. So this was reflected in the ratings of the people. So when it comes to likability and perceived intelligence, so participants actually did recognize the robot to be likable, and the perceived intelligence was also high from early on, and it did not change significantly over time. And in terms of animacy and anthropomorphism, the perception was that initially these were perceived as low. So the human participants did not find the robot to be very anthropomorphic, so very human-like, or the animacy aspect as well was not rated high. But overall, the design of the robotic coach invoked positive responses besides being acknowledged as a robot. In a way, this is not surprising given that the appearance and the functionality of the robot did not really change much across the 5-week period. And if you look at the interaction scores in terms of conversation, robot motion, and sensation, what we see is that there is longitudinal changes in the interaction score. So we see particularly for robot motion, and then in terms of conversation, actually the effect was significant, and both scores were found to increase over time. This, in a way, suggests that with time, participants found that the robot moved and interacted more consistently, as well as easier to converse with time. The third one is mindfulness sessions promote relaxation and calm in both human and robot coach sessions. For this, we use the average ratings of the 2 items, anxious, relaxed, and agitated, calm, based on participants' rating in the beginning and the end of each session. And we conducted a 2-way repeated measures ANOVA with 1 factor as the week and the other factor as the instance, being beginning versus end. And we found a significant effect of instance, meaning the scores at the end of the session were significantly higher than at the beginning of the session for both human and robot coach groups, suggesting that the sessions really made the people more relaxed and calm. But there is no observed effect over time, suggesting no huge differences in terms of time. And this could be due to various things. For instance, the sessions being only 5 weeks might not be sufficient to observe long-term effects over time. So in conclusion, the robot coach is rated high for likability and perceived intelligence, and but it's rated low for animacy and anthropomorphism, which means we actually need to work on this. So this means either we might need to improve the way the robot moves, animates itself, and acts more human-like to be able to be in accordance with the voice that's being projected by the system from the human, or we need to ensure that the voice is a bit more robotic to be able to be congruent with the current appearance and the movements of the robot. And with time, participants found that the robot moved and interacted more consistently, as well as they found the robot to be easier to converse with. So this is encouraging for us in terms of creating a robot coach for mindfulness and well-being. And indeed, this study was the first step for us, starting from teleoperated coach. Then we gradually want to move towards semi-supervised and finally fully autonomous robot coach for mindfulness and well-being. Now, let's look at the challenges when creating artificially emotional systems. So remember this nonverbal social signal image I showed in the beginning, and I did mention how we have the sender end and the receiver end. So if we replace either the receiver end or the sender end with a robot, this is still quite challenging, and there are many open research questions to be explored to really understand how this impacts the perception and the engagement of the human users in human-robot interaction sessions. So there is still a lot to research and understand there. We also need to bear in mind that this relates to machine behavior. So when we are generating response on the machine or interface or robot side, we start focusing on the machine behavior aspects. And this relates to the fact that systems learn from data. So if there are any failures on the machine behavior side, these are linked to the imperfections in the data and labels, because this is what we use as input, but also possibly the size of the data, because we use machine learning techniques. So if it's not big enough, we might not be able to create generalized models. The dimensionality might be a problem. But we also need to remember that machine behavior shapes human behavior. So we saw this with the two examples in virtual reality gaming. We saw how when the users play the very high difficulty, so level 3, how they get tense, and we start seeing this tension on their other hand and arm. But also we saw this in the other virtual reality gaming environment where the users were feeling more competent when they played the adaptive version. Or we also saw here with the teleoperated robot coach how it helped them feel more relaxed once they took the session. So in a way, machine behavior really shapes human behavior, both in intended and unintended ways. So intended, for instance, we did intend in the robot coach session to actually provide calmness for the participants and relaxation once they've done this. But in the first example, the intention was not to cause the users to move their other arm because of tension. So this was in unintended ways shaping their behavior. So we have to bear this in mind. We also need to remember that when we talk about artificial emotional intelligence, it's not necessarily exactly the same as human emotional intelligence. So machines may exhibit forms of intelligence and behavior that are qualitatively but also quantitatively different from humans. But of course there are challenges with this, because people who study the behavior of these systems are usually people who also create these systems. So they are computer scientists like me. But machine behavior needs to be studied in a broader context. So similarly to social scientists exploring a wide range of human behaviors in different contexts. So this is one thing that we need to bear in mind to really and fully understand the effect of machine behavior on humans. If you are interested in these aspects, you can find more on this in the research topic that we did for Frontiers of Robotics and AI. The research topic was called Affective and Social Signals for Human-Robot Interaction, and there are various articles as part of this collection. Also, we were shortlisted for the Frontier Spotlight Award. And finally, I would like to thank various members of my team throughout the years who contributed to this or different aspects of my research, as well as the funders that have provided the funding to bring these ideas into life. Thank you very much, and I can take now your questions.
Hello, Hatice is here with us. Thank you, Hatice.
Thank you for having me.
For the presentation and for joining us. we already introduced you, so I think there no further introductions are necessary. Maybe we can get some questions from the audience.
I can have some questions. Hi, Hatice, this is Erol.
Hello.
Hi. Thanks a lot for this really nice presentation. It was really eye-opening in many senses. I have two comments and possibly questions that I would like you to elaborate on. The first thing is you have discussed this at the end that these robots are completely different form of agents, and whereas a lot of the interaction has focused on human to human interactions, but we know that animals can sustain, like cats, dogs, and other animals can sustain really nice emotional bonding with people without being too much expressive, and without having too much of a theater of mind, if you wish, capability. So I'm just curious whether the animal-human interaction studies, are there any? That's my first question. And the second one is the way when I look at the emotions, it's more like I always think of word in reinforcement learning system. It's essentially a common currency through which you can integrate a lot of different experiences, and but when you have a reward is always related with the goal of the agent. So that means that and I am a little bit having difficulty when you say emotion, like expressing. I have not seen the goal of the agent being taken into account. You have mentioned this, that the context is important, but I believe that the context, it should be made a little bit more specific, and then that the goal of the agent, whatever it is, should also be kind of taken into account, and that's a part of the whole scenario. Thanks.
Okay, so I will start with the first question. So the first question, if I understood correctly, relates to morphology. This is quite a big sub-area in social robotics, human-robot interaction, and people are still investigating different morphologies. Even when it comes to humanoid, it's not always full body. For instance, you might have heard there are different, like Furhat robotics is not even a robot, but it's just actually a face where they project various things. Features and expressions. So the actual thing doesn't move. It's just like something like a statue in just a head, for instance. And similar other robots have been created by Hanson Robotics in the past, just the head as well, making it very realistic, even the skin and all that. So that's like one category. Then there are obviously animal-looking ones, zoomorphic robots, and even within humanoid, the size, the shape, the appearance, whether the features move or not. So there's a lot of variation, and studies are still ongoing. So it's from all these years of studying, I think there's not really a right or one single answer as to which morphology is the best for certain tasks. So for instance, it was easier if people focused on robot soccer, but even robot soccer initially started with animal-looking robots, so dog-looking robots. And there, everything is clearer because it's a game, you have rules, you know what needs to be done, problem is simplified, you have a ball with certain color, so it's easier to do image processing detection. The agents have their goals, it's a goalie, it's easier to define the goal and so on. So when it's structured this way, you would think that morphology shouldn't be a problem, but even there, initially they started with animal-looking, dog-looking robots like eyeballs, and then they moved to humanoid robots, even now style robots and so on. So this is just to illustrate that there is no single answer, even for the same very structured task in terms of morphology, because we are still learning as we are investigating. I would say it very much depends on the target user group and the problem and the application and what the goal is from the human perspective initially, if it's about human-robot interaction. So for instance, robots that are animal looking like a seal have been used quite a lot for elderly related applications, particularly in Japan. So, you know, you would pat, it will create sounds like a seal, it feels like a seal, it's furry. So this is good for stimulating the senses. Just like animals are helpful in that sense, you know, people who live alone most of the time, they would like to have a dog or a cat because it helps with, you know, you would say things even though the dog doesn't reply back to you. There is something to stimulate your touch senses and things like that. So this is just an example in terms of the needs of the application. The other example I can give is, for instance, with autistic kids, very humanoid looking robots wouldn't work because they already have difficulty understanding facial expressions. So if you have a robot that can move all of these things, it might be more confusing for them. So a robot like Pepper that looks humanoid, but none of these features move, it's pretty static, could be more helpful for kids that suffer from or are experiencing autism. So these are just examples in terms of different morphologies for different needs. So in that sense, there is no single answer as to what a robot should be. This is
may I intervene for a second?
Sure.
I was more interested in animal-human interaction studies. Like, you know, I was like, you know, because like what you said about robot is completely true. I agree, but I don't see this animal-human interaction studies. That's what I was curious.
Yeah, so I do not know that much about animal-human interactions because I have not worked with zoomorphic robots. So that's one thing I can say. So I wouldn't be able to claim expertise in animal-human interactions. I can only give examples like the Paro robot, that is this seal-looking robot, and some of these studies have been inspired by human-animal interactions, like pet. Having a robot pet is very much inspired by human-animal interactions, but it's not my area of expertise, so I can't give you the exact details of that.
No, thank you.
The second question was about the goal of the agent. So this probably was covered a little bit in the very beginning when I talked about virtual agents and I explained about these sensitive artificial listeners. If you want, I can share the slide and try to go over that, where things are simplified, of course. So I'm going to share the slide to really try to go. 1 second, share screen. Okay, so I hope you can see the screen. Yeah. So here, this was a simplified, again, system, because at the time it was a project from 2008 to 2011, so quite old by now. But there were not many fully autonomous systems that would operate only on non-verbal behavior. But here, the goal of the agents are depending on the agent. So for instance, we have Poppy. The goal of each agent is to draw each user into their own mood, emotional mood. That's the goal of the agent. Therefore, for instance, Poppy is an extroverted and happy agent. So she would try to actually speak about happy things and exciting things and would use the voice that way. She would speak faster and she would try to draw or bring the person closer to her emotional state. So make the person happy by talking about happy things and so on. Spike is an angry agent and neurotic in terms of personality. So the goal of Spike is to make the user angry. So therefore, all the behaviors of Spike are generated in that way. So Spike would cut off the person when the person is talking, would do opposite behaviors, not mimicking, but for instance, if the user is nodding, Spike would be shaking the head because wants to create tension. That's the goal of this agent. And similarly for the other agents. So here, it's a simplified version, but the goal was very much mood/emotion driven for each agent. And therefore, the analysis part doesn't change. So we still need to understand what the person is doing so that the agent can do behaviors or can generate behaviors that are in accordance with its own goals, but needs to know what the person's state is to be able to say, okay, because now the person is happy and my goal is to make the person angry, I'm going to increase perhaps the amount of shaking I'm doing and so on. So that's how it would work. So this part, the sensing part, wouldn't change. That's one example.
I agree with that, but in this, I think it goes halfway, because, like, you know, if you're an agent in this sense, and if you have a goal, and if you're achieving your goal, then your reactions would differ. For example, you know, if you're happy, and if the other person, if you are able to make the other person happy, then, you know, you will try less, for example. Or if you're angry, but the other person is not becoming angry due to your things, then you're basically moving away from your target, and you may act a little bit different. So that's it's halfway, I would say, but, you know, I can see that.
Yeah, that's fine. I'm not saying this is the full solution. So I'm just giving the example of, you know, how this has been applied. The bit that you're talking about is adaptation, so constantly adapting. So this project was not doing constant adaptation, refined adaptation. It was not, you know, the goals of the project. It was actually trying to do all of this fully automatically as the first instance. Regarding the other robotics related things that I spoke about, at the moment, we don't have the cognitive architecture in place. Particularly, I mean, I spoke about creating a robot coach for well-being, for instance. So the study that I presented here, it's very much the first study as a first step, and it's teleoperated and so on. So we don't have autonomy at this stage anyway. But the ultimate goal is indeed to do this sort of adaptation and have a framework in place for that. So one aspect that's being explored by one of my PhD students is continual learning and how we can use this for adaptation. So that's one example.
Okay, thank you.
Thank you. So I'll stop sharing.
I have a question also. Hello. My question is about that teleoperated robot study. In there, do you have any explicit effort for representation of emotions in robots, or do you directly transfer upper body motions and voice without enforcing the human coach to explicitly show his own emotions?
Yes, so since this is the first study, we actually try to project more or less what the person is doing without interfering. So it would be possible if, you know, we do want to magnify, because the movements of the robot coach are automatically detected. So you could have an intermediate step where you want to magnify, for instance, some of the aspects when you project onto the robot. So it's not a direct projection. Or you can dampen it if you want, for instance, just as an application area, for instance, if the coach is moving in a very jerky way, and you don't want people to see that on the robot because it might make people feel nervous, you can dampen some of these aspects. So instead of, you know, very fast movements, the robot can just do, you know, very slow ones. So this is possible, but we didn't interfere at this stage, and there was no explicit focus on trying to make it emotional. It was really about actually seeing how the human coach would conduct these sessions. So we have both the human and human robot aspects, and how we can actually project these things and also gather data, acquire data, so that we can train automatic models to really start doing the autonomous aspect as the next steps.
Okay, thank you.
Maybe we can stop recording and switch to Turkish and to a more informal version. Thank you again, Hatice, and we will continue in Turkish.